the constructible sense, so local systems and constructible sheets. And there's some work in progress here that on this and the relationship, especially to infinite order differential equations, which is something that's really an analytic thing. Wouldn't show up algebraically. And this uniform way, I want to mention that normal algebraic geometry will also be a special case of this approach. So it should include the usual algebraic geometry. So I should give that as an example. Okay. So let me just start from the beginning and say what I mean by evaluation ring, or field. So it's a field K equipped with a map to the positive real numbers, and it should be multiplicative. It should be non-degenerate. Of course, satisfies the triangle inequality. And the associated metric space should be complete. The definition of a Banach ring is similar. There's some slight difference here, but it's not very dark. It's not so. And some of these fields satisfy a stronger inequality. So the non-Archimedean inequality is stronger. Okay, so to each of these fields, we can associate a category of Banach spaces over K. And it's going to have a monoidal structure, which is the projected tensor product. And it will have various other nice features that allow us to do homological algebra. We get a category on K. The objects vector spaces V over K, along with the norm. So it's complete. It's compatible with the other norm, with the value. Okay, for all scalars. It should satisfy the triangle inequality. Now, if the field was non-Archimedean, we can also only look at spaces that are non-Archimedean over it. That's something that people do a lot. So you have the choice of insisting on that here as well. So there's also this category bond K non-Archimedean if K is non-Archimedean. So you just modify this condition. But if K is non-Archimedean, you can also consider this category. Either way. Okay. So we have these categories concave. Now, we can do, so we can do, so let me introduce the tensor product. So let me explain what the tensor product is. So this is the completion of just the ordinary algebraic tensor product, which comes with a semi-norm. So the element U is the infimum over all possible expressions. Over all finite expressions. Okay, and this is so you also have this internal Hong Kong here, which is just Hom VW with, so it's just the bounded homomorphisms together with the operator norm. And these are adjoint functors in the usual way, so it means it's going to end up meaning that this tensor product is right exact. Okay, so maybe I'll start with just mentioning some non-Archimedean geometry, and then I'll get to the derived part. So, okay, so just as in algebraic geometry, where we usually look at things like finitely generated algebras, there's an analog of that in non-Archimedean geometry. So for a moment, I'm going to look at this case. And we have TR. So these are subalgebras of the formal power series, and they're just defined by the condition So these R's here are just radii. So these are really the functions that converge at every point of this this disk. So this is actually a Banach algebra. It's Noetherian, and all the ideals are closed. So you can think of this as formally as an object inside the. You take this symmetric neuronal category, and you look at algebra. So whenever you have a symmetric neuronal category, you can look at an algebra object. It's an object together with the map from A tensor A to A. I mean, in this case, it's the guy I mentioned before that satisfies the usual axioms of the node. Okay, so these kind of, okay, so the basic affinoid algebra is a quotient of that Tate algebra by an ideal. So we have the category affinoid algebra. Okay, so usually in geometry we have some class of objects, and we'd like to look at topologies on this. And there's already the usual topology that people study on this guy, and that's going to end up being a special, like a case of an abstract notion. So let me just get the definition. So go ahead and do topology. We're going to look at special classes of morphism. So you can also iterate these, but there's take an object A inside here. Okay, so this is called Weierstrass localization. It's actually a dense morphism. And you should think of this geometrically as imposing this condition. So you're looking at points x, so that f of x is less than or equal to r. Okay, so you might ask, well, points where? And there's various definitions of spectra in analytic geometry, and there are points in that spectrum. So this is kind of looking at this set of points x, that f of x is less than or equal to r. It's a convex subspace. And then there's another kind of localization. So we have also a, and this one is dense. This is very different. This one is closed. So I'm adding a variable and modding out by gt minus 1, where g is some element of A. Your affinoid algebra. And this you should think of as g of x is bigger than 1. So these are called Laurent. And then of course you can iterate, you can do one of these and then add another variable and go back and forth. So this generates something called the lead G topology on the category of affinoid. It's really the opposite category to affinoid algebras. Okay, so let me mention that so Banach spaces, so these categories, Ban K and A and Ban K, are examples of quasi-abelian categories. So let me give some idea of what that means. This is a feature of a category. So category is either quasi-abelian or not. That's similar to abelian. So I'm talking here about additive categories with finite limits and colimits. So let me make a definition. Morphism is strict if the co-kernel nothing to E is isomorphic to the kernel of that nothing to the co-kernel of that. So this is always true in an abelian category. And quasi-abelian category is category with additive with finite limits of colimits, such that the strict epis and strict monos form a Quillen exact structure. So because it's a category, there's this notion of monomorphism and epimorphism. And strict is basically saying, like for instance, for Banach spaces, strict basically means the map has closed image. And this Quillen exact structure, for those of you who don't work with that, is a certain condition on these morphisms under push-ups and pullback diagrams. So this allows you to do homological algebra. But it's somehow closer to the usual homological algebra than topology is, even though Quillen structures are kind of a generalization of topology.
I'm sorry, Owen, I'm missing the verb in this sentence.
Sorry?
I'm missing the verb in the sentence. The quasi-abelian category is a category such that...
So I want to say that these collections form a Quillen exact structure.
And in your definition of strict, do you just want them to be isomorphic, or do you want the natural map to be the isomorphic?
I want the natural map to be an isomorphism. Okay. Okay, so this category product spaces is not only, like I said before, closed symmetric monoidal, it's also quasi-abelian. And in particular, we can kind of derive the tensor product. So it also has enough projectives that allow you to derive the tensor product. Both the non-Archimedean and Archimedean version have enough projectives. So let me just state that as a fact. Let me say what I mean by projective first. So definition. Object is projective if for all strict epimorphisms E to F on the is rejected. So in an abelian category, every morphism is strict anyway. It's not really a different definition. Okay, so these categories bond K, and if K is non-Archimedean, this other version both have enough projectives. And you should think of these projectives maybe I won't go into this too much, but the Tate algebra is projected as an object here. And in fact, the Tate algebra is a co-product, but in a different category. So these projectives are basically co-products of K, but these categories don't have co-products, but their closely related category does. So I'll write less than or equal to 1 are projectives. These are good examples of projectives. They're also flat, where we use this contracting category. So this means that not only do the morphisms have to be bounded, but they have to be of norm less than or equal to 1. Okay, so now I can finally state a theorem, which is kind of the starting point. Let me say one more quick definition, and then I'll say the theorem. So let's see the closed symmetric Noidal category with enough projectives, quasi-abelian with enough projectives. So let's call the morphism A to B. We'll call. So here these are algebras. So I mean in COM-C, these are maps of algebras. So if you look at commutative unidal associated monoids in C, and you look at a morphism there. So we call this a homotopy epimorphism. So this homological algebra, the quasi-abelian category, allows you to derive the tensor product. And there's a natural map, and it should be an isomorphism. So you can think of this as two different statements. One is that the ordinary tensor product is D. And second, that there's no higher torus. Okay. Okay, so here's a theorem. I saw it from Kobe Kremnitzer. So morphism affine algebras. It's a homotopy of the morphism. And even to say that, I mean that I'm thinking of it here. So in the bond A, let's take the non-Archimedean version for it. If and only if so it's some combination of those Weierstrass and Laurent localizations of the floor. I mean, you can iterate them and do whatever you want. Kind of combination. So another way to think of this is that on the level of the spectrum, which I didn't introduce, this is an open set in that building topology. Okay, and I should remark that if you look instead at just the category vector spaces, and instead of finite algebras, you just take finitely generated algebras, you'll get a Zariski, you'll get the same theorem is true, it's not true to us, but the same thing is true, and it will be a Zariski open. So this is an example of analytic and algebraic geometry kind of coming together, because this condition makes sense, this first condition here, makes sense in many different contexts. If I change this closed symmetric category, I can write here vector spaces. Then, if these are finitely generated algebras, this will be a Zariski open. Okay. And you can also characterize the issue of when something is a cover. So, you know, you might have a collection of finite algebras, A to Bi, which geometrically corresponds to something like this. And you'd like to characterize when it's surjected in some kind of categorical way. You can also do that, but I won't get into that now. I have other things I want to say.
When you define the Laurent localization, you allow the radius to be 0?
No, I think no, bigger than 0.
But then how do you get Zariski open sets as localizations?
How do I get open sets?
Zariski open sets.
The Laurent business is only in this non-Archimedean case. So if you take if you take your vect, okay.
If you take your function g that was in your that you had in the Laurent definition, you were allowing all points with absolute value of g was bigger than r. You don't want to just require g to be non-zero?
I think R is always non-zero. Let me think for a second. So I'm not saying that like this proof goes through for vector spaces. I'm saying that this condition of homotopy epimorphism, it also makes sense in the category of vector spaces, convent, and that it gives the Zariski opens. I didn't think about literally taking R to 0 or something.
Well, what norm are you taking? Maybe you're taking a trivial norm? Is that what you're doing?
No, I'm not. It's not a special case. It's like a separate case. So
I was just thinking, if you took a trivial norm, then I just wondered what that would do with the issue of what's that here.
yeah, I mean, okay. So
What you were just saying.
So you have this category. Then you have C as vect K, and in both of them satisfy this condition. So it makes sense in both of them to talk about homotopy epis. But the open sets you get are completely different in nature. So in other words, if I was to rewrite this theorem and here I wrote convect, what would the explicit description would be completely different. They look completely different.
Now, I wasn't referring to the main part of it here, just the equivalence with the two bottom lines.
This is like the definition of the G topology, but I think I understand what you're saying, and I didn't really think about it that way, so I don't want to answer right now. But I understand what you're saying to kind of see it really as a limiting case. I never thought of that. It's true that if you take the discrete topology, which we allow on K, then this is kind of inside here. So,
That's what I'm saying, yeah.
A vector space, you can think of it as a Banach space with the discrete topology over any field. I don't think I want to allow R to be 0. Anyway, let me move on. So one, let me mention two things that are kind of unsatisfactory about this picture. So One is that I'm only looking at non-Archimedean fields, and I said from the beginning that I wanted something that worked over any field, so maybe the complex numbers. Let me say bad things, or things that could be improved. So one, what about complex analytic geometry? So in complex analytic geometry, there is a version of the Tate algebra. Probably Jonathan has worked with to see this. So you look at formal power series, say in one variable. So that's sum of AI x to y, such that the sum of the coefficients is less than infinity. So you can do that, but this is a non-Noetherian algebra. It's recursive. So that's one thing. And the second thing is that there's an issue with the Durand cohomology.
Non-material.
With even in the non-Archimedean things, and it was addressed by. So there's a kind of way out of this. So one solution. The issue is that you get bad answers. So you get bad answers. So Grosser-Koenig, what he said is, let's look at overconvergent functions. So you're still thinking geometrically of the same closed disk. So you're looking at functions that converge on some slightly larger disk. And because it can be any larger disk, no matter how slight, it's really a union of functions, of these Banach spaces. You want to take some kind of union of Banach spaces. Banach spaces don't have unions in any kind of categorical way. So you'd like to give it some other structure. So I'll mention Gambosi. So he worked Grosser-Koenig's work with morphological structures. I'll say more about this in a moment. So really, I'm throwing out the functions that are not analytic at these boundary points. You're throwing them out. You're saying it has to be analytic at these boundary points. So it's really some sub-algebra of your algebra, but it's a union of other Banach algebras. Okay, so both of these issues can be solved by looking at these overconvergent functions. So what you can do is you can look at overconvergent functions over any evaluation field, including the complex numbers. And it all makes sense. And you never really have to deal with these algebras that I said were bad, only in some kind of limit. And in that limit, you'll get the same answer whether you work. If the field is non-Archimedean, you'll get the same answer. So really, you're going to look at some co-limit of Tate algebras. Okay. That's what you'd like to look at, just for the disk. For radii, say rho is bigger than r. I'd like to look at some kind of thing like this. And so what we do is we look at this category in Banach spaces. So the objects are category has all the same properties as Bogdan. Wait, maybe I should say the morphisms of two guys. So let's go from this way. These index sets have nothing to do with each other. Are morphisms of pre-sheets. So this category, it has all the same properties. So for instance, the tensor product will just be defined in this dumb way. You just put together the index sets. Okay, so again, we can repeat the same story, looking at algebras and so on, and now these kind of over-convergent functions are algebra objects. And so we actually proved a similar theorem to the one I said before. So let me. Oops, I guess I switched that over. So again, I'll just write heuristically. So again, and this time it's over any field. So in this case, k can be equal to the complex numbers. And in which case, you're talking about complex analytic spaces together with a certain topology of compact Stein domains. Okay, so that still looks a little bit different from what people usually think of in complex analysis, because these are still including their boundary. And so we introduced a class of Stein algebras. So let me mention that. And then I still didn't get to the derived picture. So I'll say the Stein very quickly. Actually, this was just these two people. Stein. So for Stein algebras, you'd like some kind of exhaustion by those guys. So again, to such a thing.
Can you say again? I didn't get what you said about the topology. A closed set or the open set?
They're open in the sense of a growth-ending topology, but they're closed in the sense that they include their boundary if you draw out their points in the complex system. So depends how you want to say it. They're
So
open.
you have the open ones and the closed ones, or only the closed ones?
No, they're open in the sense of the Grothendieck topology, so they're the thing that appears in the covers, but they're closed in the sense that if you write out their spectrum, it includes the boundary.
And a union of those or a limit of those is going to be one of those?
It's a Grothendieck topology. It doesn't have to satisfy that axiom. It's not a topology in the standard point set.
Yeah, I know.
The union is not, infinite unions are not. Okay. But now I actually do want to take unions. So, okay, so maybe I should say one thing. So, these bornological algebras are kind of inside here for a very obvious reason. That so what you have is, like, say, for instance, the colimit over rho bigger than R of the Tate algebra of radius rho. So it's kind of already an in system. So these algebras that appear in this over-convergent functions, they're kind of automatically appear. But now for Stein algebras, we're dealing with the opposite kind of limit from the point of view of category theory. So now, instead of the spaces getting, instead of looking at smaller and smaller spaces that are like a little bit bigger than some fixed radius, I'm going the other direction. So I'm looking at bigger and bigger spaces and exhausting some kind of picture like that. So the definition of a Stein algebra is you take affinoid algebras, and you'd like to take some kind of limit. And the nice thing is that in this category, limits also exist. So here, what I want is a limit where each of these is an affinoid algebra. Like I introduced before. So I want each morphism is a bias stress localization. And finally, I want that the interior of the spectrum, which I'm not introducing now, but there's some topology on the semi-valuations introduced by Petrovich. This is kind of a technical condition that M of AI is inside M of AI plus 1. Oh, did I go? Sorry. So this is contained in the interior. So this would be M of AI minus 1. Okay, so that's saying that you're really changing at each point. You're not fixing any. You're not maintaining any points. You're actually getting bigger at every level. Okay, so for instance, we have a similar theorem to that one with Kremnitz here as well. And so we can, in particular, recover the standard metric topology on a complex manifold or complex analytic space, just using this condition as well that I wrote before, using the Dirac concept on it. So I'll just write kind of casually this, like over C, say this would recover the topology of the complex, of the metric topology. This is really much more complicated than this story because these limits are all going in the wrong direction. Okay, let me quickly get to what I was supposed to talk about. So, about the derived analytic story. So in derived algebraic geometry, we want to kind of maintain information about things like non-transversal intersections. So when we were intersecting two subvarieties, we'd like to do a derived intersection, which corresponds in algebra to a derived tensor product. And of course, the derived tensor product of two algebras is not an algebra. It doesn't really make sense. You have these higher tors, they have to come from somewhere. So you can use differential graded algebras or simplicial algebras. So here we want to work with, you can use negatively graded chain complexes or simplicial algebras. The simplicial guys are nicer because the tensor product works term-wise. So this is it's actually a monoidal monocategory. So I'll just give the definition that we use for the model structure. So if I take all projectives inside the bond, it's actually enough to work with just bond, but that then you can get yourself a simplicial set, or i.e. a topological space by Hamming from P into X dot. Then this should be a weak fibration or weak equivalence of simplicial sets for all projectives. Is a fibration equivalence of simplicial sets. Okay, so for people who have studied derived algebraic geometry, you need to put a topology, of course, on the affine objects. The affine objects are, say, simplicial or differential graded algebras. So for the affine objects in this flavor of derived analytic geometry, you just take I'm going to take the strictly commutative algebras in S and bar. And take the opposite category. And so let me say, first of all, theorem that S in bond K satisfies the axioms of HAG, of Toyn Bertozzi. It means that you can do algebraic geometry with respect to it, and it turns out that you get, as I've explained, analytic geometry out of doing this relative algebraic geometry with respect to this guy. And of course, a formal Zariski open in this picture, again, it's just this condition. This is now, completed because it's all coming from end bond. It's completed and derived. And you can define like cotangent complexes, entalomorphisms, derived stacks using their technology. See what else I want to say. Okay, I'll end there.
What are the compact objects? Category of modules.
In this category.
Yeah. Category of modules.
I think the coherent or finite modules.
No, the coherence cannot be compact. Right? I mean, already in the non-directionality, the coherence are not compact.
Inside the category of modules?
Yeah.
I'm not sure actually.
But so in particular, we don't know if the cotangent complexes are perfect or not.
So the cotangent complex, it does agree with what you would expect for, say, a complex manifold. That is a computation we've done.
Yeah, so you just get the cotangent complex of the complex analytic space.
Yeah.
If you do it for your
Yeah,
for
yeah.
logical guys, you'll get the cotangent
Yeah,
complex.
yeah.
Oh, so it's not perfect in any way.
Based on a smooth, it's.
On a smooth, yeah, but
no.
on a singular one, it's not going to be perfect.
Yeah, no.
There's got to be some condition on the derived structure that guarantees that the cotangent complex is perfect. It's a finiteness condition.
You mean in the amplitude or?
No, locally finite type condition.
Okay. I see. I understand what you're asking.
Is there any sense in which simplicial in-Banach algebra is locally finite type?
So I want to just say maybe this would help, like the formal relationship between algebras or diagrams of algebras and the cotangent complex goes through. So the universal property goes through, and you can prove a lot of things using that. So an affine. So if you take AN, take some diagram of ANs and take whatever homotopy, code is not, it will commute with the cotangent complex functor. So that would imply this finiteness.
No, they're just going to tell you that the cotangent complex satisfies descent in your topology. It's not going to tell you that it's perfect under some condition.
I expect that. I expect that if it's certainly the analytification of a finite type algebraic variety, then it would be perfect. So.
No, that can't be true. If you don't put a derived structure there, then the tangent complex.
No, I mean the derived analytic.
Yeah, but then it's a condition on the derived structure. But the question is, what's the condition on the derived structure?
Okay, yeah, I'm not sure.
Okay. Yeah.
So you mentioned you can define Stein space in your context. So do you have like analog of Oka principle?
Remind me what that is.
So basically, it says for Stein space, the category of
vector bundles is the same as the smooth.
Smooth.
Category. Well, I don't know what smooth means in the non-Archimedean setting. So I don't know what the category of smooth vector bundles is in the non-Archimedean. It would be very nice to have something like that. So really, it's not. To have examples, you would need that. You would need to decide on that first.
But if you don't do derived geometry, if you just do underived analytic geometry with your chronological guides and the Stein compacts as your ordinary topology, you were saying that your definition of Stein recovers the ordinary definition of Stein.
At least the topology is the same, but you don't get all Steins. I mean,
Right, but do you get any, so you get restriction factor from coherent shifts in the ordinary topology to coherent shifts in your topology. So does this have any derived factors, or is it exact?
no, that should be an equivalence.
So that's an equivalence.
Yeah.
So that solves this major problem that you cannot do normal analytic geometry with Stein compacts because the restriction factor actually has a lim 1. And you're saying in your case, if you replace the Stein compacts with your Steins, which are these filtered limits, then it won't have that lim 1.
Sorry, I guess I misunderstood what you mean by restriction. You mean restricted to the guy.
I'm just saying, start with a coherent analytic shift and analytic
Yeah.
space.
Yeah,
Pull it back to your side.
yeah,
And view it as a coherent shift for your Stein guys, which are the filtered coordinates.
yeah, that for a
Now,
coherent.
is that factor exact or not?
That would be underived. There'd be no derived
Okay.
factors. Yeah.
Okay, so it solved that problem.
Yeah.
Okay. Well, thank you.